Hi everyone, I'm Anoop. Unfortunately, the lecture today could not be put online, so we'll be discussing some lecture highlights. We have been on the topic of mechanics, talking about forces and power. And in the class today, we discussed two examples, one of a particle moving under constant force and a particle which is moving such that a constant power is given to it. And we solved for its position and velocity as a function of time. We'll repeat that derivation here. To start with, the basic information in hand we need is F is equal to ma. Force is mass times acceleration, and acceleration is rate of change of velocity. So you can write it like this. And the velocity is rate of change of its position. So you can write it as a second derivative of x. For these examples, we'll be considering a particle which is only moving in one direction, that's called that x direction, and it's really important to have a proper sign convention, which means the forces in this direction, the velocity in this direction, and the acceleration in this direction would be taken positive, and opposite to this direction would be taken negative. So what does this equation tell us? This tells us that if a force is acting on a particle, its speed would be increasing with time. Its acceleration, it's accelerating, so the velocity is increasing with time. And if the particle is more massive, then for the same force, if the particle is more massive, the change in speed, acceleration would be smaller. But the speed is increasing, so that means the kinetic energy is increasing. So half mv square is increasing. And few days back in the class we derived that the rate of change of a kinetic energy of a particle is this quantity called power, which is defined as force times velocity with proper sign convention. We'll use these two equations. And first one, let's take a particle which is moving with constant force acting on it. And if the force is constant, the mass is constant, the acceleration is constant, so that means A is a constant. On a graph, this would look something like this, that with time, the A is constant, a straight line. And A is dv over dt, so dv over dt is a constant, let's call that A. And we can integrate that out by taking dt on the other side. And we get v is at plus some constant of integration. And if we use the fact that at time t equal to 0, the velocity is 0, then these initial conditions gives us that c is 0 and velocity is equal to at. And how does that look on a graph? So velocity is increasing with time linearly, it's 0 in the beginning, and the slope of this line, tangent of this angle, is a. We can further use the fact that velocity is dx over dt, so dx over dt is a, is velocity, velocity is a times t, and integrating that out, dx is a times t times dt. X gives a is a constant, gets out, t dt is half t squared plus a constant of integration. And using the fact that, using the initial condition that x is equal to 0 at time t equal to 0, this gives me that x is equal to half at squared and the c is 0. And how does that look on a graph? X is a parabola. It's increasing like this. One interesting thing to observe is this: the velocity is integral of a, and like this. Time t equal to 0, velocity is 0, time t, velocity is v. So this term, which is v, is integral a dt 0 to t. This is nothing but the area under acceleration time curve from point 0 to t. So that means the velocity is nothing but area under acceleration time curve, and that makes sense because at any time t, this area is a times t, so velocity is at. Similarly, the x graph is area under velocity time graph, so at any time t, the area of this triangle is half times t times velocity. Velocity is this, so that's half times t times at, which is half at squared, and that's like this. So each curve is the area under the previous curve, and inversely, velocity is derivative of position, and that's a slope. So velocity is the slope of this curve, acceleration is the slope of this curve. For this curve, the slope is constant, so acceleration is constant. For this curve, slope initially is 0, velocity is 0, and the slope is increasing, so the velocity is increasing with time, linearly. Furthermore, looking at these two equations and eliminating t from them, so the t is v over a, and if I put that t in this place, I get, by rearranging, that v square is 2ax. And these three equations, 1, 2, 3, they are very important for motion with constant acceleration, like a particle falling in gravity is moving with constant acceleration a equal to g, and these equations become very handy, so you should remember them. Furthermore, if I multiply this equation both sides by half m, I get half mv square is half cancelled with 2, so ma times x, which is force times x, and if I take a derivative both sides, I get is force is a constant, and the derivative of x is v, so this is nothing but our power equation. So now let's do a particle which is given a constant power. Power is force times velocity, which is mass times acceleration times v. So that means the acceleration of the particle is p over mv, and acceleration is dv over dt. So that gives us p over mv, and we can integrate that out as usual, taking v on other side, and integral of v dv is half v square, and p over m is a constant, moves out, t plus c. And if we use the initial condition that v equal to 0 at time t equal to 0, I get, by rearranging this expression, c is 0 and 2 goes on that side, 2 pt over m is velocity is given by this expression. And how does that look on a graph? At time t0, velocity is 0 and it's increasing with time. This is another kind of parabola. Another thing to notice is that at time t equal to 0, velocity is 0, so that acceleration is infinite and the force is infinite, and acceleration is a slope of velocity time curve, so the slope at this point is infinite, it's vertical. That is a little bit unrealistic, but we'll just take that case. And furthermore, velocity is dx over dt, so dx over dt is 2p over m, and writing p as t over half, 1 over half, and integrating that out. So when time t equal to 0, x is equal to 0, time t equal to t, x is c is x, and I'm using definite integral, so no need for constant of integration, and I get x from 0 to x, 2p over m is a constant, and this is 3 by 2 by 3 by 2, and time is going from 0 to t. And if I put those values, I get x is 2p over m times 3 over t, 3 over 2, and 2 over 3. And how does that look on a curve? As time t is increasing, the position is increasing something like this. It's the area under that curve, though it's a little bit difficult for us to calculate. So in this case, and this is very similar to the bicycle problem in the homework, in this case we solved our differential equation like this and differential equation like this by hand, but we could also do the differential equation numerically, for example in MATLAB. And let's take this equation and do it numerically. So the P was acceleration, dv over dt was P over mv. And we already know that the answer looks something like this. But to do it numerically, we should know what a derivative is. And the definition is that if you take some general time ti, and if you increase it by small amount delta t, the velocity is also increasing by some amount delta v, and the slope of this line, which is delta v over delta t, which is delta v over delta t, if I make delta t very small, shrinking to 0, then this thing approaches the definition of dv over dt. But we definitely can't make it close to shrinkingly small in numerical methods, so let's approximate this by delta v over delta t itself. So the derivative is approximated like this, and better we are if we take the delta t smaller, which can be limited by various things. Like if you make it really small, it'll take huge amount of time to integrate it. But anyway, so also we need to divide this interval of time, and let me say I do it like t0, t1, t2 and some general ti, and they are equally spaced, though it's not important, it's not needed, but let me take equally spaced, and that equal time interval is delta t between these two. So if I look at this equation, I get delta v over delta t at time I is p over m v at time I, and this delta v over delta t at time I is v at time I plus 1 minus v at time I divided by delta t is equal to p over mvi, and I can rearrange this equation and write it as vi plus 1 is vi plus p over mvi times delta t. So a differential equation like this, using finite approximation of the derivatives, can be reduced to a difference equation. So this is called a difference equation. What does it do? It does that if you know the velocity at time I, then you can find the velocity at the next time step I plus 1. So all we need to know is the velocity at time t equal to 0, and using this equation over and over again, we can find the whole velocity profile. So with this equation and velocity at time t equal to 0 is 0, we can get that whole profile. But if you look more carefully, there's a small problem here, that velocity at time t equal to 0 is 0. So that means this thing at time t equal to 0, if you put 0, this is going to become infinite. That means velocity at time I plus 1, t1, would be infinite. But that's not true. The velocity at time would be something small. So one way to avoid that problem is, don't assume that v is equal to 0 exactly. Take it as a small number such that these terms come out to be small. The more you can do is by taking these steps and writing a MATLAB code and then playing with different values of vi initially. MATLAB has other kind of inbuilt functions like OD23 and a whole series of ODs which can solve these differential equations for you, but we wanted to do them by basic method like that. I hope you understood it well, and if you have any problems, any questions, please come to the officers.